The topic of the session today is AI algorithms. So we're considering algorithms in the context of artificial intelligence and how algorithms learn from data. And it is my great pleasure to welcome Professor Claudia Plant to introduce that topic today. Claudia Plant is professor in the Faculty of Computer Science. She's head of the research group Data Mining and Machine Learning. And her research focuses on data mining, broadly speaking, information theoretic data mining, big data, methods for complex heterogeneous data, scalable data mining, and applications of big data and data mining, machine learning across some different disciplines: medicine, neuroscience, environmental sciences. Professor Plant, without further ado, thanks very much for taking the time to be with us today, and the floor is yours.
Thank you very much, Lucas, for the kind introduction. So hello, everybody, and I will jump into the topic right away. I hope you can hear me well. I hope everything is working. And then I will just continue. And my agenda for today is that I want to introduce you to the basics of AI algorithms in just a nutshell, in just one lecture of about 1 hour. So I will start with a motivation. Actually, I want to address the question, why do we need algorithms that learn from data? And by giving you this motivation, I will also a bit disentangle the several notions or wordings which are flying around. For instance, data mining, machine learning, AI, and data science. And I will try to clarify a little bit what each of these means. Then I will give you a basic introduction to algorithms in computing. So we just need to know what basically an algorithm is. Next, I will show you the specials or the special challenges that are emerging from applying algorithms to big data. And finally, I will introduce you to decision trees, which is a special type of an algorithm, which is quite easy to understand, I guess, so I hope so. This gives you a flavor of how an algorithm really works on data analysis. And finally, I will wrap it up with a summary and an outlook. So as all of you probably know, we are currently observing a data flood. So tremendous amounts of data are generated every day in various applications. So there are a lot of different applications, from biomedicine, like molecular data, medical data, from astrophysics, that is that the telescopes are getting larger and larger and the imaging quality is increasing all the time. So you get more and more data. Also in business, you get a lot of data from online shops or from transactional data representing users buying some goods. Or also in the web, you can observe click streams of user, and users are generating a lot of content in form of social media. And the manual analysis of all this data is, of course, infeasible, and also simple statistical methods come to their limits. Therefore, advanced research areas like machine learning, data mining, data science, and AI have emerged. And in principle, you can distinguish two types of basic goals. One first goal is descriptive modeling. That means you want to explain the characteristics in your data, and you basically want to understand or get an overview of massive data. And the second goal goes beyond that understanding, and it refers to predictive modeling. That means that you want to predict the behavior of new data based on some model which you have built on your data you have today. You want to make predictions for the future. In both tasks or goals, it is important to notice that the extracted models or patterns don't have to apply to 100% of all the cases. It is really, the thing is that if you would construct a model which covers 100% of all your cases, you would run into a severe overfitting, and you get the same problems again, that your model would have an excessive size and is completely not understandable anymore. And therefore, we in data mining or machine learning, we always looking for a very good abstraction of the data, preserving the most essential characteristics of it, but not all of them. And actually, these methods, machine learning, data science, data mining, are currently really transforming science. So essentially, the way how scientific discoveries are made today in many disciplines is driven by data analysis methods. And therefore, a data-intensive science is often called the fourth paradigm of science. So already in ancient times, people observed natural phenomena, and this refers to empirical sciences. Later, in the last couple of 100 years, there has been emerged a theoretical branch of sciences using models, most commonly mathematical models, explaining some phenomena. And here on the slide, you see, for instance, one of Kepler's laws that explains how the planets move on the sky. And therefore, you can predict, based on this law, when seasons will come again. So when will it again be summer, for instance? These can be predicted using this kind of theoretical branch of sciences. In the last few decades, there has been emerged a computational branch of science with increase of computational power. It has become possible to simulate even very complex phenomena. For instance, the formation of galaxies or the expansion of the universe. And these simulations, you input in there both sources of the data, essentially the empirical data, but also the laws or the theoretical rules. And then you can simulate new data. And later you can then compare the simulations, the simulated data, to the real existing data and come up to conclusions if your models accurately match the phenomena you are observing. But this kind of matching or understanding of data originating from empirical observations and from simulation can also not anymore done by hand. You need data analysis methods from machine learning, data mining, that essentially can help you to get an understanding of all this data which you have. And you need these methods for the data captured by your instruments, but also the data generated by the simulator. And both sources of data need to be processed in the computer by software. And then the scientist needs to analyze the results of the methods and can come up with some new conclusions. So as I said, scientific breakthroughs are nowadays really empowered by advanced computing methods in different areas. So in earth sciences and environmental sciences, when you think about the climate change and, for instance, predicting weather and climate phenomena, you need really algorithms on operating on massive data, but also in health and well-being. For instance, people from the Human Brain Project, they try to understand how the brain works by using data from observation and from simulations. But also in citizen sciences and in political sciences, these sciences involve more and more data analysis. And of course, also in basic natural sciences like physics at CERN, you urgently need analysis techniques for making sense of all the data which is produced by the instruments like the Large Hadron Collider. And notions like machine learning, data mining, and also artificial intelligence are often used interchangeably. And there are many definitions out there, but essentially there is no clear definition. What machine learning and AI have in common is that these notions are motivated by the fact that algorithms in certain domains arrive to have capabilities that are matching human performance and often even outperforming humans on very selected tasks. So unlike humans, the computer never gets tired or bored. It can always process and analyze data. You of course have to keep it running. You need a lot of electricity and hardware, but besides that, it never gets tired. This is a strong benefit. Also, computers can take many more factors into account when making decisions as humans. Nevertheless, I would not say that they are really intelligent. And in the end of this talk, I hope you will understand better what I mean. Rather, I'm convinced that the capabilities of humans and of artificial intelligence or computer algorithms running on computers are kind of complementing each other to achieve certain tasks. And there are a lot of related buzzwords or fields. Data mining, machine learning, and AI has also a lot to do with these fields like applied mathematics, statistics, databases, information retrieval, and we need high performance computing to scale up the algorithms really to massive data. And many of you have heard maybe also about the notion of data science. And data science is kind of an umbrella for all these different buzzwords, and it integrates all techniques and all scientific directions that are being concerned with data analysis. And also it also contains new computational paradigms and hardware systems. So many of the efficient algorithms of today, they run on graphic processing units or on clusters of such machines, which enable very high parallelism, which was not possible before. And therefore, by the explosion of data combined with advanced computing paradigms like GPU clusters, you can do nowadays things which are not possible a couple of decades before. And to wrap it up, many sciences worked on the topics from the last decades. And when you ask a statistician, he or she will probably tell you that they are doing data science already since hundreds of years. And of course, this is somehow true. However, just by the involvement of the computational power and the open data or explosion on the internet, many scientific discoveries and also business concepts are possible today. That's so far for a little teaser or introduction. Do you have questions so far? If yes, then you can type in the chat. If it's okay, then I will continue by telling you what are algorithms in computing. There is a question, how are models defined? Yes, in several ways, basically. Mostly when you have a problem, you need to define it in some way formally or mathematically. And then you need to break it down to an algorithm which can be executed on a computer. And now I will tell you what kinds of algorithms can be executed on a computer. And the following couple of slides follow a bit the introduction of the first chapter of a very common book to algorithms in computer science. This is the book of Thomas Corman, Liaison, Rivest and Stein on algorithms. And you don't need to read it, but I just want to put the reference here. As Lucas told you already, an algorithm is a solution to a computational problem. And a computational problem can be specified by an input and output relationship. So first of all, you must, when you have a real world problem, you must clarify for yourself, how does the input to that problem look like? And furthermore, you need to address the question, what should be the output for each input? One example would be that you want to sort the names of people in an alphabetic fashion. In this case, the input would be a list of the names of all the people, and the output would be the same list, but now sorted in an alphabetic fashion. So when you are kind of designing an algorithm, this is the first step you need to clarify. And an algorithm is a tool for solving a well-specified computational problem of this sort. And algorithms must be or should be correct. So that means that for each input, they produce an appropriate output. And algorithm also must be efficient. That means they should run as quickly as possible and use as little as memory as possible. So indeed, memory is the storage capacity of your computer, and it is not infinite, but you can only input a limited amount of data and output a limited amount of data at some particular time instance. And therefore, it's better when your algorithm is memory efficient, meaning that it does not consume so much memory. And so an algorithm is a well-defined computational procedure that takes some value or set of value as input and output some value or set as values. And often we as algorithm designers write algorithms down in some kind of pseudocode, which is a set of statements, and that can then be later implemented in a language of the programmer's choice. And yeah, an algorithm is correct when for every input instance, it ends with the correct output. Then we can say that our algorithm solves the given computational problem. There are unfortunately also incorrect algorithms which might not end at all at some points, at some instances on the input, or which might output an answer which is wrong. But in the following, we are just considering correct algorithms. So there is also a notion of a problem and an algorithm. A problem is more in our common sense, the instance of the problem we want to solve. So for instance, we want to solve the problem to convert the weight of a person in pounds to kilogram. And an algorithm for this problem to solve it is a procedure that explains how we can solve it. So first we need to read in the weights in pounds. Second, we need to calculate the weight in kilogram by the formula that the weight in kilogram equals the weight in pounds multiplied by 0.45. And finally, as a third step, we print out the weight in kilogram. And a computer program is a computer executable description of an algorithm. That's what we have seen here. This description is just a pseudocode-like description, and it has to be translated to some specific programming language, like for instance C or Python, to become a computer executable program. And here you see the problem solving process. In the beginning, you have a problem. You analyze this problem. You end up with a problem specification, which you can write down in an algorithm specified by a pseudocode. then you have to implement this algorithm, meaning that you have to transform it into some programming languages. Later, this implemented program is compiled by the computer, which means that a sequence of machine executable statements is generated by a software, also called, that's also an algorithm. It's a software called the compiler. And finally, this compiler, it outputs an executable, which is a program that you can run on your computer. First you have the problem. You would need to describe it as an algorithm, as a sequence of instruction describing how to solve the tasks. And then you can implement this algorithm in some programming languages like C++ and get an executable which you can then run on your computer. And what are the components of an algorithm? So what type of instructions or things are inside an algorithm? So you have variables and values. You have sets of instructions, sequences, and so-called procedures or functions. And procedures are some sequences of instructions. And we can use these elements also in the pseudocode to make sure what are the elements of an algorithm. And we will see in a second a simple example which makes this more clear. Furthermore, we have selections that are instructions which decides which of two possible sets of sequences is executed next. Then we have repetitions, or also called loops, which means that some instructions are repeated multiple times. And finally, which is also an important part of a program, is the documentation. This is annotations by the programmer that specify what the algorithm does at certain places. Let's look at a very simple algorithm. As an input, this algorithm takes a sequence of n numbers. And n here is also a kind of a variable. So we don't want to consider one specific number of numbers, let's say 10 numbers or 12 numbers, but we want to have a general algorithm which works on any cardinality of the numbers. And the numbers are stored on the computer in a sequential fashion. We computer scientists call this an array of values. That just means that the n elements are stored sequentially in the storage. So we have a t from 1 representing the first number, t from 2 the second number. And now we want to have an algorithm that outputs the smallest number among our m numbers. And this algorithm is here written in a pseudocode-like fashion. So it starts by assigning a variable called min to the first number in our sorting. And now we have a loop. And this loop starts with a keyword for. It's also that same keyword in many programming languages. For I equals 2 to n, we do if, and this is a branching, if our current number ti is smaller than our so far minimum, we set this variable min, to the number ti. And so we run from 2 to n through all of the numbers. And whenever we find a number which is smaller than the minimum so far, we assign the variable min to that particular number. And this statement is written in brackets, indicating the loop for repetition. And finally, we output this minimum number. And the performance or the runtime of this algorithm is a function of our n, and n is the number of elements we are looking. Because the algorithm looks at every element in our array once, we need some time to access it and to look if this is smaller as the so far known minimum. And therefore, the algorithm in terms of its runtime depends linear on the number of elements n. So this is a very simple algorithm, but you can see, or you can maybe imagine that can be transferred to machine readable statements via compiler, and then it can be executed on your computer. And of course, it is very nice that computers do not get bored or tired. So if you give them millions of numbers to detect the minimum, they will do that. Don't give this task to some human. And this is some very small introduction to what an algorithm is. Of course, when you have a given problem, you need to select an algorithm. And often it is the case that you don't have to invent that algorithm on your own. For instance, when you want to do classification of emails for spam, there are well-established algorithms you can just use. And you can just choose among them. However, the choice of the best algorithm for a given problem is a challenging one. After having you explained what is an algorithm, I want to give you a flavor of the challenges when designing algorithms for big data. So maybe you have all heard about the buzzwords of big data. And essentially, it refers to some characteristics of data that are often present simultaneously in nowadays data. So you have a huge volume of data, often many terabytes. Just imagine a very huge volume. Often you have temporal data which comes with high velocity, and that requires real-time processing. Finally, you often have a high variety of your data, which means that you have data from heterogeneous data types and from heterogeneous sources. And finally, the veracity or trustworthiness of the data is often also not really clear in the beginning, and there are different sources of different data quality. And therefore, we nowadays need to develop new approaches to data analysis. Some examples from my applications which I'm dealing with. For instance, in medical applications, you are considering functional magnetic resonance images of the human brain. And these are time series of three-dimensional volume images of the human brain. And they are really massive in terms of the size. So the data for one subject is often several gigabytes. And the velocity and the real-time analysis is needed in many cases. For instance, in a joint project with partners from Munich Neuroradiology Klinikum Rechts der Isar, we have been working on a project for real-time analysis of pain perception from EEG data. That is very interesting and important, since for the monitoring of anesthesia, it is very important to know if the patient has still pain or how deep the anesthesia is. And when you want to do a real-time analysis of the data, you need to have algorithms that really process data from real-time EEG just in milliseconds, since data are arriving at a tremendous speed. And also in medical applications, you often have the variety of data types that need to be integrated. For instance, transcriptomic data and metabolic data in order to get to a better understanding of diseases like schizophrenia. You want to find links between these different data sources. Now, let's give you a very short introduction to basic data analysis tasks. So basically, we in machine learning data mining distinguish between two types of tasks and also algorithms. The first type is typically supervised. And these are methods that learn a given target variable. Mostly these are classification methods, and we will just later in this talk see an introduction to decision trees. And also very popular are today deep neural networks. And supervised classification means that you have given a target variable that you want to learn. For instance, you want to learn if a person is suffering from some disease or if he or she is healthy. And you are building a model based on data you have, and then you can classify new persons. And also what different type of method is the unsupervised machine learning or data mining. These are mostly clustering methods, but also association rule mining or outlier detection methods and methods for frequent pattern mining. And here you don't have a clear analysis goal, but you just want to find any kind of regularity or pattern in the data. Let's look into the classification problem. Here you are given a set of instances or data objects and a set of predefined classes. And the classification problem is that you learn a mapping or in mathematical notation, a function which goes from the set of instances to the set of classes, and that outputs for each instance exactly one class. And here you have a data set called the training data, and you use this data set to learn your classifier, to build your model. And this is a toy data set only consisting of 5 data instances. But you can learn from this data set a very simple classifier. So the task is to predict the risk of having an accident based on the age of a driver and the car type. And you can see that you successfully can classify your training data into the classes without any errors if you just use these 3 simple rules. So if one person is older than 50, then he or she tends to have a low risk. And also if it's a truck driver, so LKW is a truck, then the risk is also low. But if the person is young and drives some other car, the risk tends to be high. These are just some simple rules which can be inferred from your training data, and we will see in the decision tree how we can do this inference. An important problem of supervised learning is the validation of the model. So as I said, you have a training data. You use an algorithm that builds a model on that comes up with some classification rules. And then you want to know how good this classifier is. And for this, you need some further data source for validation, which is called the test data. And this is data for which we also know the class label. And later we can check if the classifier was correct, yes or no. So this toy problem is a bit of a different one. It's based from the university, based on the rank and the number of years a person works on the university, and also maybe based on their names. We need to build a classifier which outputs whether or not this person has a permanent position at the university. And likewise, we come with 2 simple rules that correctly classify our training data. Next, we can use some test data for which we also know the labels. For instance, chef, professor, and for years. We put this onto our algorithm. Our algorithm would say that yes, chef is a tenured person. And then we check whether this is correct. And by looking at the class label of this person chef, we can find out, yes, the classifier is correct. And therefore we can, now we can output some statistics like the classification accuracy, which is the number of correctly classified instances. And this is how we can validate supervised data mining or machine learning methods, and that we have some training data, which is data with known class labels. And from this, the classifier learns its models, and we have some test data, and that is data with class labels that are used just for evaluation of the models. To just give you an impression, in unsupervised learning, a common task is clustering, and that is that we want to group our data objects into a natural grouping structure such that the objects belonging to the same group are more similar to each other as the objects belonging to different groups. And clustering requires a notion of similarity or distance, but we don't need any labeled training data. And a clustering algorithm generates a categorical variable which represents the cluster assignment for each data object. And for instance, when you have these data objects here, you would group them into two groups, which are here on the slide, marked by different color of the objects. And you can see that we have a high intra-cluster similarity, which is evident by short distances between pairs of objects that are within one cluster, like the two green objects here. And we have a low intercluster similarity, meaning we have a high distance between the pairs of objects, which are assigned to different clusters. And the evaluation of this kind of methods is much more challenging since we don't have any class labels. And there are different approaches. One approach is that we just take our clustering result by the algorithm, and then we reorder the distance matrix according to these clusters produced by the algorithm. And if the algorithm works well, then we see that we have a blockwise structure in this matrix representing clusters that have a high intra-cluster similarity and others areas where points in different clusters have a low similarity. Okay, then I have given you an introduction on what types of algorithms we have that process big data. Next, I will go to give you some more flavor, to dip a bit deeper inside, to show you how a decision tree works, which is an example algorithm for supervised learning. Are there any urgent questions? Okay, then let's jump inside. Also, the task is supervised learning, so it's a classification problem. We are given a set of data with known class labels. Again, here you find such a data set, data table. And here the goal is based on the continent of a country and its population to predict what is the most favorite sport in this country. And we have a training data for which we know that. And the goal is to build a model that predicts the label of new data. And the decision tree is such a model. It is an algorithm for classification. Indeed, it is a hierarchical system of rules that is learned from the training data. For instance, one data point of the training data is Spain, Europe, 46 million, and soccer. And it serves for classification of new data. And how can we classify a new data item? For instance, Pakistan, Asia, 182 million population. We insert this new object into the root. We see the first node asks ourselves if the continent is South America or Europe. No, this is not the case. Therefore, we go down this path. Then we have a split, a test on the population. And since the population of Pakistan falls into that area, our algorithm predicts that the favorite sport of Pakistan is hockey. What do you think? How useful is this algorithm? It depends on the quality of the training data. As it is not very useful. So indeed, maybe you know that the favorite sport in Pakistan is not hockey, but instead it is cricket. But this doesn't matter. In general, it is that we have built this model on a very limited training data set. And that's the reason that it's not so accurate and that's not very well generalized to new or unseen objects. But let us look a bit in more detail what the tree is and how we can build such a tree in the computer. So essentially, we can distinguish between inner nodes and leaves. Inner nodes represents tests on one attribute, and the attribute is a column of our data table. And each of these tests splits the data into two parts. And the leaves represent the predicted class of all data objects, which are going into that branch or finally into that leaf of the tree. And now we are looking for an algorithm which constructs us a good decision tree from the training data. So the task of learning is to find a good decision tree from a given data table. So we need to select what is inside the inner nodes, and we need to select how to build the tree. And there are two goals for constructing a good tree. The first goal is that we want to keep the height of the tree as small as possible for two reasons. One reason is very obvious, and that is that we want to have a runtime efficient classification. Because the larger our tree is, the more time it will take to perform this classification. And when time is critical, we want to be fast. Furthermore, when we have a small height, we are more robust against overfitting. So when the tree is very expanded, it really covers every single data case of our training data. And as I said in the very beginning of this talk, we don't want to have a model that is correct or that covers 100% of our cases, because that is essentially overfitting. And it will hurt us because we have then a bad generalization to new or unseen data. And this is one goal, that we want to keep the tree small. However, we have a second goal, and actually these goals are conflicting a bit. We want to have class pure leaves. So the leaves should be consisting of only objects of one class, or only training data of one class should go into each of the leaves, because then we know that we precisely have modeled our data distribution of the training data. And this is a prerequisite for correct classification of the test data. What to do about these two goals, which are essentially conflicting? So actually, we need really a clever algorithm for constructing our tree. And current algorithms for constructing decision trees build the tree in a bottom-up fashion and use carefully selected tests for the inner nodes. And there we are back in our design process, from a problem to an algorithm. So essentially now we are studying the problem, how should I build a good decision tree? And we are trying to arrive with an algorithm, which is a sequence of instructions which describes how I can do that task. And this algorithm I later can implement in a programming language of my choice, and I can get an executable program, for instance, a C program. When designing an algorithm, it is often, I would say, a stepwise, loop-wise procedure, and it is always good to get a feeling for your problem. So essentially, the central idea of all existing decision tree construction algorithms is that we need to carefully select our splits in our nodes in order to arrive with mostly class pure subtrees. So essentially what you can see here, that are some diagrams where I just color coded the class distribution of your data inside the nodes. So essentially in the root nodes, you have all the data objects from our training data table. And this table consists of 11 objects. And in color coding, you can see the majority class in our training data is soccer, followed by the classes cricket, hockey, and baseball, which are the smaller ones. And our first split is continent equals South America or Europe. And when we go down to the left subtree, we can observe that this left subtree already is much more class pure. It only consists of mostly consists of soccer instances, and there are some cricket instances also. And when we split it further down, we get to class pure leaves. Okay, so it is a good idea to design splits which enhance the purity of our subtrees. That is clear. But now we need to do this in the computer. And a computer cannot live with such visualizations. It cannot inspect the diagrams and compare the colors of the different options. And therefore, we need a mathematical formulation of our concept, which is class purity. And one of such formulations is the so-called Gini index. And sorry, now we have some mathematics, but informatics is a word which stands for mathematics plus automation. So what is inside many algorithms is a lot of mathematics indeed. And the art for algorithm designers is to find a suitable formulation of the quantity we want to judge. And the Gini index is such a suitable formulation. So you find the formula right here. So the Gini index of our training data is 1 minus a sum, and the sum runs from j equals 1 to the set of classes, and it sums up the squared probability of each class. And the probability is the fraction of the training data belonging to that class. And a small Gini index represents a class pure data set. So because when you just have only one class inside that, you actually don't need, you sum up, here you have one term just, and this is 1. So 1 minus 1 equals 0 in the case of a maximum class pure split or data set. And when you have a large Gini index, you have a common mixed up of all classes. And now we can also evaluate a split. And a split creates us a partitioning of our training data into some subtrees. In our case, we just consider 2 subtrees. And the Gini index of the split is the weighted Gini index of the subtrees, weighted by the size of the subtrees. That is just the TI divided by T is just the weighting by the size. I hope this is more or less clear, but often an example helps very much. So imagine we now want to select what is essentially the root, what is essentially the best split for our tree. Here we have one option that we essentially use this split for the population. And first of all, we compute the Gini index of our complete data set. And then we compute the Gini index of each resulting subtree. And next, we do the weighted summation. And here for this option, we arrive with an overall Gini index of 0.47. And for another possible split, we get an overall Gini index which is larger of 0.59. And when we compare this, now we can give an algorithm that the computer should just use that split which has the better Gini index. And then I can give you the flavor of the tree construction algorithm. So this algorithm could be noted in the following pseudocode. Do until the tree does not get too high, compute the Gini index of some candidate splits and select the one with the lowest Gini index and grow then the tree by one level. It is kind of an algorithm. However, it is way too unspecific since many things are still not clear. Do until is okay, but the tree gets not too high. We must be much more specific if we want to have a sequence of instruction that can be executed at a computer. We must somehow define the height. And one option of defining the height is, okay, we can do that until all leaves are last pure. But as I said, that will generate an overfitted tree. Therefore, most existing algorithms have some threshold on the purity of the leaves. And that must be much more clearly specified. And then compute the Gini index of some candidate splits. Indeed, there are many possible ways to split a node. Indeed, you can even say that's an infinite number of split which is possible. Think of a numerical attribute as a continuous attribute. Let's use, for instance, age of a person as an example. You can split the tree into two subtrees after every age which occurs in your training data, and these would be many splits. And so age is not really a continuous attribute. We call it an integer valued attribute, because in general you consider the age of persons being 18, 19, 20, and not 18 years .7 or .8 or whatever. But for really continuous attributes, there is even an infinite number of splits. And therefore, we must specify what we mean by some candidate splits. And it's a consideration of runtime, how many candidate splits we want to examine. So you see that there are some more choices which need to be made. But finally, this is then an algorithm and can be translated to a computer program. And now let's look into a decision tree, a real decision tree built from medical data. So this is the problem which was studied here was the classification of breast cancer based on cellular measurements. And this is a paper from Nature Methods Medicine from 2016. And there you can see that decision trees, albeit they are, I think, quite simple and quite easy to understand, are still very powerful classifiers because they have a very important benefit, and this is their inherent interpretability. So you can visualize a decision tree, you can visualize the inner nodes of it and the leaves. And from this tree, you can come up with two interpretable rules which involve difference of the attributes. So for instance, the first rule is if the A3 uniformity of the cell shape is smaller or equal some threshold, the head stands for end. And the second measurement, A2 uniformity of the cell size, is quite large. And the blend chromatin, which is the seventh attribute here, is smaller or equal than some threshold. You have a benign sample of the tissue. So these are nice interpretable rules. Okay, and maybe you have heard a lot about deep neural nets, because that's a topic of what people are talking a lot today. That is, these classifiers have the benefit that they are even much more powerful, and they can be applied to even very difficult classification problems if you have enough training data. And it works pretty well, for instance, for natural language processing, for translation, and for even generating really realistically looking natural images. These methods perform surprisingly well. However, they are currently more like a black box, and the classification decisions and also the learning of this model is very complex and very difficult to understand. And a decision tree is a tree of hierarchical decisions, and the neural net is a graph or a network of different single decision-making instances called the neurons. And this network is also very much densely connected or even fully connected. Yeah, there are some questions about the decision trees, and I will answer these questions now. Yeah, one question was on the computation of the Gini index. So the weighting in this example is not equal because it is that we have in total 12 training instances in our data table. I think I said 11 previously, but indeed, yeah, 12 if you look at the little table. And in the first split, 6 instances go to the left and the right subtree, and in the second split, we have 5 instances going to the left subtree, and 7 instances going to the left subtree and 5 to the right one. And it depends, of course, on the split, how many instances go to which subtree. And as I said, you can select the split as you like. And you can also have one subtree just consisting of one single instance. And of course, the Gini index of this subtree would be 0 because it's just class pure. But then you would create another big subtree with all of the remaining instances. And therefore, we have this kind of weighting criterion for the size of the subtree. And there's another question, which is on the tree construction. How can I tell if a particular tree is too high or not? Thank you for this very good question. Indeed, you need a labeled test data set to tell so. So when a tree is overfitting the training data, it is too high. It essentially covers every single data instance of the training data, but its classification performance on an independent test dataset will not be good. And for this reason, people use an also labeled independent test dataset to judge the generalization power of this tree. And after that, they shrink the branches, and then you try to cut the tree down to reduce the height, and you reduce these branches where you lose only very little in classification accuracy. Are there other questions to this part? If not, then there's another question. Okay, what is the difference between inference and prediction? So inference is often a term that is used in statistics literature. Prediction is more used in machine learning literature. And prediction really means that you basically predict the class of a new data object. Statistical inference can mean anything. It can refer to descriptive statistics, but also to prediction. Okay, let's give you a summary on what I talked today. So I would say, I hope I can convince you that artificial intelligence in terms of algorithm is something completely different to human intelligence. And sometimes people have a bit fear of algorithms, how they are transforming our lives, and I can of course understand that. But I must say, I would hope that everybody would have a basic knowledge of what an algorithm is and what are the strengths and limitations of algorithms. So first of all, it is us, it is humans that design algorithms. And also when people today say algorithms are self-learning, I would not completely agree to that. So I would agree that algorithms can learn depending how you teach them to learn. So humans make algorithms that can, to a certain extent, self-learn, but it's not completely self-learning. What is very important is that the data is the basis of how algorithms learn. And you must be very careful in the data acquisition. So essentially, it could be that data is highly biased. And when algorithms learn from biased data, the results of algorithms will also be biased. For instance, algorithms tend to be biased in the sense towards certain minority groups. So towards certain gender groups, but also racial groups. And the problem is often not that the algorithm is biased, but the data has these biases inside. And it's a question of current research, how to come up with fair algorithms that somehow correct the bias in the data before they learn. It is indeed a requirement that we really need algorithms. So we need algorithms to make sense of big data. So we cannot live anymore without algorithms. Therefore, I think it's very important that we try to design algorithms for social good. So for the well-being, for the benefit of the society, for the well-being of people. And this requires intense collaboration of computer scientists like me with non-computer scientists. And therefore, I just also accepted this invitation because I'm very much interested to tell people who are non-computer scientists, to give them a basic understanding what algorithms can do and what they can't do, because I think many issues are due to misunderstanding. And what I gave you to read, as Lukas Schlögl mentioned, is this paper, which which identifies some essential factors of how to design algorithms for social good. And I must also say that I see it very critical that a lot of money is spent in the military domain, for instance, and not all people around the world are working towards algorithms for social good. And I'm happy that I'm working here at that university, and that I'm only involved in this kind of projects that are really to the benefit of the society. So in terms of medicine, in terms of renewable energy, this is very essential for me.